we're going to go over the video analysis lab post-lab notes. So let's begin. Okay, so let's go over the three things that I asked you to create. The first one was a x position, y position time graph, and this was simply you were just seeing where the ball was at moments of time. And so if I were to use this, it will look something like this. And so for every moment of time, we were able to locate the path that the ball took as it traveled through the air. Okay, now the big importance behind this idea here is what we're seeing is the path of travel of the ball. But the big main important idea for this unit is that you understand that as the ball is traveling through the air, okay, this is the big idea here. The object has a y velocity and a x velocity, okay, and these are actually separate velocities. Okay, but when we view the object, we don't view them as separate velocities. We view them as the total velocity. So, for example, when we first launched the ball, we knew that the ball was traveling like up and to the right. Okay, and at the peak, the ball was traveling forward a little bit, and when it landed, it was traveling like down and to the right. So this is how we view the ball when we look at both the Vy and the Vx simultaneously. But for physics, we can't look at Vy and Vx simultaneously from the start. We actually have to break it down so that we are looking at the x components and the y components separately. So one of the things I asked you to do was create a position time graph that looks like this. So if you did it correctly, your position time graph actually gave you a linear graph, like so. And this is a same graph as unit 1. And this was the buggy lab, okay? So the big idea here is that for a position time graph, the slope is velocity. Okay? Not only is your slope velocity, but your velocity for our x-axis, unless told otherwise, unless there is air resistance, your velocity for the x-axis is constant. Okay? And as a reminder, just put it right there, this is the buggy lab. The buggy lab moves with constant velocity. And so the slope should always be linear. We have a linear slope with constant velocity, and if our velocity is constant, remember, this was before we actually discovered what acceleration was, and our acceleration is 0 meters per second squared. This is huge, okay? And so if this is your position time graph, our velocity time graph for the x-axis, it'll be a flat line. Now, a couple of important things, because this will pop up more and more and more, we know that the slope for this velocity time graph is equal to acceleration, and because it's a flat line, there is no slope, it's 0. But the other important thing is that the area under the curve is equal to your displacement. Okay, so just in case in the future we see questions about area under the curve, that will be the highlighted portion there. All right. Now, what about the y versus t graph, or the vertical position versus time graph? So this is our vertical position versus time graph, and if you did it correctly, it kind of looks like our main graph, like so. Okay, but there's a couple big main important parts that I want you to identify. The first part is this part right here that I just highlighted. This is the rising motion. Okay, that's a rising motion. And here the ideas are the same. The slope is still your velocity. So at the end, your slope is small. And in fact, as we rise to the peak, your velocity approaches 0 meters per second. So that means that according to the vertical components, it's not moving up or down at the peak. It's just moving forward. At the very beginning of the throw, okay, we have a big slope. So this is big slope. And this is important because at the beginning, we are moving pretty fast. Okay, so another big idea here, and I'll do this in a different color, is that if you take a look at the shape of this position time graph, we have a slowing down motion. So this must mean that our velocity was positive because we have a positive slope, but our acceleration is negative. Okay, and so hopefully you're putting a couple of pieces together. All right, now what about the latter half? I'll do this in a different highlighter color here. Oops. It's the same exact thing. So this latter half right there. So let's just break it down. Our velocity at the peak is still 0, but we can see here that our velocity is pretty big. We have a big but negative velocity. Okay, so here what this means is that we're actually speeding up. So we started off with the velocity of 0, okay, and then over time our velocity became more and more negative, and so that must mean that our acceleration is also negative. So this is huge, this idea right here. Okay, and this is something that we discovered before in previous units, but it's coming back again. What is this negative acceleration? Well, before we answer that, let's create our velocity y versus time graph. For velocity y versus time graph, we have something like this. We start off with a positive velocity, we approach 0 midway, and we end up with a negative velocity. So here, we have a negative slope. And this negative slope is your acceleration due to gravity, and that negative simply means that it's going down. So our slope should have been pretty close to 10 meters per second squared. However, if you remember, if you plugged in your data table for this graph here into Google Sheets, the formula that it gave you, I told you to try to compare it to one of the kinematics equations. And so the kinematic equation that it most likely resembles is the one I'm about to show you, which is xf is equal to xo plus v initial t plus 1/2 at squared, where I think Google Sheets doesn't have t's, but rather x's for the x-axis. But you should see some number, some constant times x plus 1/2 or plus some constant times x squared. But if you remember, I asked you to just replace those x's with t's. And so this shape is showing you the kinematic equation, xf is equal to xo plus v initial t plus 1/2 at squared, where this value, whatever Google Sheets gave you, okay, it should have been 1/2 a. So hopefully Google Sheets gave you something that was close to -5. Now, if it didn't, that's fine. We made a lot of assumptions and a lot of jumps and rounding stuff when we were doing our scaling. Okay, so hopefully it was close to -5, -5 t squared, but if not, that is a-okay. But for velocity y versus t, I didn't ask you to create this, but the slope would have been -10 meters per second squared. Now, same ideas, area under the curve, I'm going to highlight it here. So we have this highlighted portion. So this is the vertical displacement, okay, as it was going up, and this right here, this is the falling. This is the falling displacement. So one of the things that I want you to see is that the amount that it went up is equal to the amount that it falls. And that should make sense, right? Because if it left my hand and it goes up and it falls back to the same height, our vertical displacement is 0. All right, so those are the big main ideas for this unit. One thing here is that we see here our velocity halfway is 0. That's important. And the other idea here is that your velocity for the horizontal, okay, it looks like this. The velocity for your vertical looks like this. And here your acceleration is 0, and here your acceleration will always be -10 meters per second squared. And that's it. That's our post-lab analysis. Watch the next video where I go into a really long detail of how to solve these problems. See you next time.